All right, so here we are in section 2.3. We're dealing with set operations here. And the idea behind this section is basically creating new sets out of old ones. Up until this point, we've been focusing more on relationships between sets. For example, to say that A is a subset of B, like we talked about in section 2.2, is establishing a relationship between two pre-existing sets, A and B. It's not combining the two sets in any way, however, to produce a new set. And that's what we're doing with set operations. So to sort of motivate this, let's think about operations with real number arithmetic. So, for example, the statement 2 plus 3 equals 5. The addition that's happening here, the plus, is what's called an operation. And the idea is that it's taking two real numbers, the numbers 2 and 3, combining them in a way using this operation to produce a brand new number, which is 5. What we want to do is something similar with sets. We want operations that will take two sets and in some way combine them or do something to them that produces a third and new set. Okay? And there's going to be a total of 5 operations that we discuss here. In fact, one of them we've already discussed, the complement of a set is an operation. That's an operation that's performed on one set, however. It doesn't combine two sets. The rest of these operations will take two sets and perform an operation on them. So the first operation that we want to talk about is what's called the intersection. An intersection of two sets, A and B, is a new set that contains only the elements that A and B have in common. Okay, so the intersection of two sets is the set of elements that they have in common. Symbolically, the way that we denote the intersection of two sets is with this upside down capital U. And notice that it appears between the sets A and B, much like the plus symbol appears. Symbolically, we can define the intersection this way. The intersection of A and B is the set of all x such that x equals A let me back that up. Not x equals A. X is an element of A, and x is an element of B. The key word is and here, because we're going to also define the union of two sets, which you see down here, in a way that looks almost the exact same, but we replace the word and with the word or, which gives us a very different set. But the key thing here is that if x is an element of this intersection, then it has to simultaneously belong to both A and B at the same time. Compare that to this next operation that we want to define, a union of two sets. So if we have sets A and B and we want to create their union, the union is the set of all elements that appear in either of these sets. What you can think of it as is basically taking a bucket and then taking all of the elements of A, dumping it into that bucket, and then all of the elements of B and dumping it into that bucket, and everything that's combined in there forms the union of A and B. And that kind of makes sense with the terminology. A union of two things is what you get when you put two things together. We denote the union of A and B as A, then something that looks like a right side up, capital U, B. Symbolically, we can write that this way. Notice, very similar to the definition of an intersection, but we say that the union of A and B is the set of all x such that x is in A or x is in B. What this means is that elements of the union of A and B don't need to belong to both sets simultaneously, although they can. X could belong to both A and B at the same time, but at the very least, we just need x to belong to one or the other. So it's going to be a little easier to see this if we do this example here depicting both of these sets using Venn diagrams. So let me start with A intersecting B. What does the Venn diagram for this look like? We start by creating our universe, a little smudge right there, U. And A and B are two sets within this universe. Now, I don't know if A is a subset of B or if B is a subset of A, so I'm not going to draw one set completely contained inside the other as we would in a subset relationship. And we also don't know if A and B are completely disconnected. We'll come up with a term for that later. It's called disjoint. And we'll look at the Venn diagram for that as well. So kind of the most general way that A and B can be related here, and this may not be the case depending on what A and B are, but without any more information, I'm going to assume that A and B both belong to this universe, and I'm going to draw it as though they overlap in some area, but not completely. Okay? The intersection of A and B should be the set of all elements that belong to A and B simultaneously. That's the same thing as looking at this overlapping region right here. So that shaded portion would represent the intersection of A and B. What about the, sorry, I wrote the wrong thing. I wrote union when I was talking about intersection. A intersection with B. I should have used the upside down U for that one. Let's do the union of A and B over here. Same thing, I want to draw my rectangle representing this universe. Didn't necessarily mean to make that rectangle bigger than that one, but that's what we got. And in this general case, we're going to draw A and B as overlapping but not completely. What is the union of A and B? Well, if X belongs to both A and B simultaneously, then that's sufficient for it to belong to the union, as this definition implies. However, elements don't need to belong to both sets simultaneously. They could just belong to B, or they could just belong to A. And in any of those three cases, the element that we singled out would belong to the union, because the union contains everything that appears in either set or the other. So I would be shading in everything from both sets when talking about the union. Okay? Just like that. That would be the union of A and B as a Venn diagram. Let's kind of do the same thing. Look at unions and intersections, but with sets that we have written out for us in one form or another. So starting with this, I want to find the union and the intersection of each pair of sets given in this example here. Here, A is equal to the set containing 1, 3, 5, 7, 9. B has the elements 5, 6, and 7. What is the intersection of A and B? Remember, we're producing a new set from these two old sets. And this new set should contain exactly the elements that A and B have in common. That's what the intersection is. Well, the only elements that A and B have in common are the numbers 5 and 7. You can see that appearing in both sets. That would have to be the intersection of those two sets. What about the union? Well, the union of sets A and B is simply the set of elements that appear in either set, either if it's in common or if it only appears in one of the two sets. Or in other words, again, think of the bucket analogy. Take a bucket and dump everything from A and everything B into that from B into that bucket. Now here's kind of something important. I'm going to write out what the union looks like. 6, 7, 9. This is the union of these two sets. And one thing I want to make clear here that's somewhat of a flaw in the bucket analogy. If these literally were objects that I were able to dump in a bucket, then that bucket would contain the number 5 twice, because the number 5 appears here, and it also appears here. But if you notice, I didn't list the number 5 twice. And that goes back to something we discussed when we defined sets, which is that sets can only contain each element one time. You cannot have copies of the same element showing up more than once. So if you have repeats, if you have elements that these two sets have in common, you don't list them twice. You only list them once. So 5 and 7 are only showing up once, even though they appear in both sets. Okay, we're going to do the other examples, but I want to point something out that's interesting here and worth noting. Notice that the intersection of A and B, which is the set 5 and containing 5 and 7, happens to also be a subset of A as well as a subset of B, because the elements here are contained here and they're contained here. That is true in general of any two sets. The intersection of any two sets will automatically be a subset of both of them. Okay? Now that's not true of the union, but in a certain sense, the reverse of that is true. Look at the union, 1, 3, 5, 6, 7, 9. That's a very large set compared to these two, and it is not a subset of either of them. Notice this set contains the number 6, which is not contained in A. This set also contains the number 9, which is not contained in B, so this is not a subset of either one of these. However, A is a subset of this union, and B is a subset of this union as well. So unions will contain both sets as subsets. Not something that we're going to be focusing heavily on here, just an observation, okay? Let's look at the next example. Notice this one is given different notation. We're not using roster notation. In this case, the set A is the set of all real numbers that are greater than or equal to 4. That's what this set is talking about. B is the set of all integers. If you remember, the set with the symbol Z represents the set of integers. We defined that previously. So what is the intersection of these two sets? A intersect B. I now can't compare element for element what these two things have in common because I'm not able to list all of these things out. Both of these are infinite sets. But let's look at the intersection. So this is whatever these two sets have in common. Well, if an element belongs to the intersection of these two sets, one thing we know about it is it has to be a number that's greater than or equal to 4. But it also has to be an integer. So that means I can't put numbers like 4.1 into this set, because even though 4.1 is greater than or equal to 4, it's not an integer. With a little bit of thought, you should see that this set looks like this: 4, 5, 6, and so on. Okay? Now, just to verify, all of these numbers are integers. This is still an infinite set, which the ... indicates, and we discussed that before. But also, all of the integers in this set are greater than or equal to 4. This would account for all of the numbers that satisfy both of these conditions, or fit in both of these sets. Now, the union is trickier. A union B. And this is going to have a pretty unsatisfying answer. Remember, unions don't have to only take in the numbers that these two sets have in common. The union will contain everything that belongs to either set or the other. I don't have a way of listing these out. Even with the ... notation, I can't list out all the real numbers greater than or equal to 4. And that has to do with a property that's very advanced with real numbers called density. We can't list them the way that we can integers. Not an important term for you to know, but it turns out that the best way to indicate the union of these two sets is to literally just write this. I basically rewrite both sets with a union symbol. Very unsatisfying answer because it seems like we didn't do anything. But it turns out this is really the most efficient way to represent this union. You rarely need to do this in this class, but this occurs on occasion where there's not anything that we can really do to better write the union of two sets. We're not going to see that again in this example. All right, let's take a look at C. Notice that C has two sets that we've previously defined. So again, that R and that Q, those represent specific sets that we mentioned in a previous section. R is the set of all real numbers. Q is the set of all rational numbers. What can we say about the intersection of A and B? Well, remember, this is the set of all numbers, or all elements that A and B have in common. But one thing I know about rational numbers is that every rational number is also a real number. Or in other words, the set of rational numbers is a subset of the set of real numbers. So literally everything that's in Q is already in R. And so that means that all of the elements here are exactly what these two sets have in common. The intersection of these two sets is Q itself. Because, again, the list of all numbers that are in common between these two sets are exactly the set of all rational numbers. What can we say about the union of these two sets? Well, again, the union of these two sets is the set of all elements that we would get by throwing these two sets together into a big bucket, right? But consider this for a moment. If I took all of the real numbers and dumped them into a bucket, and then I took all of the rational numbers and dumped them into a bucket, or the same bucket, is this set contributing anything new to that bucket? Well, the answer would be no, because as we said before, this set already contains all of the rational numbers in it. So by dumping Q into that bucket, there's nothing new going into that bucket. And because we don't repeat, or we don't list repeats like that, we already have the entire union after dumping R into the bucket. That means the union would be the set of all real numbers in this case. Now here we see an important relationship, kind of similar to what we observed up here. We observed a connection between, subsets and these unions and intersections. In this case, one of the sets that I was combining with the other happened to be a subset of the other. So B in this case is a subset of A. We haven't had that relationship in the previous two examples yet. It turns out that if you take the intersection of two sets and one happens to be a subset of the other, the intersection will equal the smaller set. That's what we got here. If you take the union of two sets where one is a subset of the other, then the union will be the larger set. And that's always going to be true. If you sit and think about it for a minute, it should kind of come to you why that's the case. Okay? Last example. Here, these two sets look very different. One of them contains letters, one contains numbers. What would the intersection and union of these two sets be? Well, notice in this case, if I'm looking for the intersection of A and B, I'm looking for what these two sets have in common, but they have nothing in common. They're completely non-overlapping. And so that means their intersection is the empty set. That's one of the reasons we need to have an empty set. Because if we didn't have something called the empty set, we wouldn't have any way of denoting this intersection. They have nothing in common, therefore their intersection is the empty set. The union, again, is exactly what I would get by putting everything from set A and set B together into one big set. So there's nothing really fancy about that, okay? Now this right here leads to an important definition that I hinted at earlier, the definition of the term disjoint. If you have two sets that don't overlap, meaning they have no elements in common whatsoever, then we say that those two sets are disjoint. But another way of defining disjoint sets is to say that the intersection of those two sets is the empty set. I'm giving you that definition right up here. Okay, so again, A and B are said to be disjoint if they have no elements in common, or equivalently, that's the same thing as saying that the intersection of A and B is the empty set. Let's look at that relationship between disjoint sets in the form of a Venn diagram. So here, I want to create a Venn diagram for two disjoint sets, A and B. What would that look like? Again, we always start with our universe, U. Now, before, when I was doing Venn diagrams, I said that the most general case is to draw A and B as we did in these two examples, where they overlap somewhat, but not completely. But if two sets are disjoint, that means there is no overlap. So that relationship would be indicated this way. Here's set A, here's set B. They don't overlap at all, indicating that they're disjoint. Okay? So up until this point, we've discussed three operations that we can perform on sets, and we're not done defining these operations, but I want to take this time to look at how we would combine those operations. And those operations are complements, which we discussed in section 2.2, and then intersections and unions, which we just defined and took a look at. So not only can we use these operations to combine, one or two sets, but we can also use them in conjunction with each other. We can use multiple operations all at the same time and use that as a means of combining sets into new ones. So here's a few examples to discuss what I mean. In this case, the universe that we're looking at, U, is the set of integers from 1 to 8, 1 through 8 here. A, B, and C are given here. Okay, so these all contain some subset of elements from U, because that's the universe. I want to look at different ways that I can combine the sets A, B, and C using these operations we've defined. So let's start with this one. This is the set A complement being intersected with the set B. What does that look like? Well, I know that an intersection is the set of all elements that these two sets have in common. And I know what B looks like because it's given to me up here. I don't know what A complement looks like because it's not shown up here, but I have enough information to find it. So I know that A complement is the set of all elements that are from the universal set, but that don't belong to A. Well, if A contains the numbers 1, 3, 5, and 7, notice that's the odd numbers from U, then A complement should contain the even numbers from U. That would be 2, 4, 6, 8. Okay? Knowing that, I can now take the intersection of this set with B. So compare this to B. The only number that A complement, and I think I said A and B, A complement and B. The only number that A complement has in common with B is the number 8. So that would mean that A complement intersecting B gives me the set containing the number 8. And that's it. That's the only thing it would contain. Okay? Here's a more complicated one. And notice we're using two operations again, a union and an intersection, but I've included parentheses here. Those parentheses function the same way that they do with real number arithmetic. They tell you what to do first. So if I'm doing multiple operations like I am here, I need to make sure I'm looking at the parentheses first. The very first thing I need to do is determine what the intersection of B and C are. Okay, so I'm going to go and look at the intersection of B and C, and I'm going to see that B and C actually don't have anything in common. They're disjoint. So that would mean that their intersection is the empty set, as we just saw with the definition of disjoint sets. So then how do I use this in the larger problem? Well, A, the union of A with B intersect C, notice that's the same thing as the union of A with the empty set, because we just determined that this is the empty set. But what does that actually mean? Well, again, think of the bucket analogy. If I take all of the elements of A and dump them into a bucket, and then I take all of the elements of the empty set and dump them into the same bucket, the union is what I have as a total in that bucket. But the empty set doesn't have anything in it. It has nothing to contribute. So this union will only consist of the elements of A, which are 1, 3, 5, and 7. That's it. Nothing else. Okay? Let's take a look at this one now. Again, we have a set of parentheses which says do this first. I have the union of B and C, and then once I've found that union, I'm supposed to take the complement of that resulting set. So what is the union of B and C? We have to start there. B and C were disjoint, but that doesn't tell us anything about their union. The union is just the set of all elements that we would get by putting these two things together. That would be 4, 5, 6, that's C there, and then everything from B as well, 7 and 8. Okay? The complement that I'm looking for, complement of the union of B and C, is going to be the set of all elements in our universe that are not found in this set. That would be the numbers 1, 2, and 3. Okay, so that answers that question. Now, at the end of this section, we're going to explore examples similar to this one in a little bit more depth. We're actually not going to do more examples with it, but there's another way of looking at this using something called De Morgan's laws. We can actually turn the complement of this union into an intersection of the complements of B and C. I'm not going to dig into that quite yet because I'm going to wait until we get to De Morgan's laws, and then maybe we'll take a look at this example to confirm that. one last example. This is the most complicated one we've dealt with so far. A, or it's the intersection of A with the intersection of A complement and B complement. So let's start with the parentheses as we normally do. But even starting in the parentheses, I have two sets that I haven't shown or that I'm not given up here. So I first need to determine what these complements are. A complement we found back here. It was 2, 4, 6, 8. So I'm going to list that out. B complement. What should B complement be? Well, if B is the set of numbers 7 and 8, then its complement is the set of numbers in our universe except for 7 and 8. So that's going to be 1, 2, 3, 4, 5, and 6. Okay? Now I need the intersection of those two sets. What is the intersection of A and B? Again, we're looking at what these two sets have in common. Well, the complement of A has only the even numbers from U, and so that means the intersection of these two sets would be everything that I can find in B, the complement of B, that's even. 2, 4, 6. Okay? Now that we've done that, we've determined what the set in the parentheses looks like. I'm supposed to take this set and find its intersection with the set A. A intersect A complement intersect B complement. Now we're looking at the set A, which is up here, and trying to find everything that it has in common, because that's what an intersection is, with this set that we found here. However, A consists only of odd numbers, while this set contains only even numbers. So they don't have anything in common. Those two sets are disjoint, giving me the empty set. Okay? Now we could actually make that determination much earlier if we think about it, if we sort of talk through it. And this is not something I'm expecting you to do, but once you become really familiar with sets, this is something that you may have been able to determine much more quickly. Right away, I already knew that this should have been the empty set. And how did I know that? Well, look at this set in parentheses here. It's the intersection of two complements. That means that anything that's in this intersection can only consist of elements that belong to both of these simultaneously. In particular, everything in this intersection has to belong to the complement of A, as well as the complement of B, but more importantly, the complement of A. However, nothing in the complement of A will appear in A itself. That's from the definition of these two things. So there's no way that their intersection can contain any elements. Right away, I know that that should be the empty set. Again, you don't need to think through it that way. It's better to kind of do this more procedural way of approaching these problems. Okay, that's as much time as I have for this video. In the next video, we're going to be doing a lot of the same thing, but with Venn diagrams to see it from that perspective as well.